should let Adam give his talk. I'm very grateful that he could offer to give a talk on short notice on cryptography. So I won't steal any more of his time because he has a deadline as well. So take it away, Adam.
All right. Well, glad to have this opportunity to tell you all about this project, which, full disclosure, doesn't have any VST element at the moment, though in the past at least, there's some discussion about adding a VST backend to it. As far as I know, no one did that yet, but hey, this could be the impetus for it. So this is a project done with a few students shown down at the bottom of the screen here, and it's about cryptography. Let me be a bit more specific. So let's talk about how secure web browsing works. So your web browser wants to talk to a web server. The web server has a cryptographic public and private key, along with the certificate saying whoever knows this private key is the following entity. And the browser, to start talking to the server, goes through what's called the key exchange protocol to establish a shared secret. Afterwards, there's a symmetric key known only to these two parties. But the browser still wants to know that it was talking to the right party there. So it gets a hold of the public key and the certificate and challenges the server to prove that it knows the private key through a digital signature. And the browser can check that and make sure that everything is legit here. And after that, we can have the main communication be carried out using symmetric crypto algorithms, which are faster than public key algorithms, using the symmetric key that was agreed on. So this is going on every time you see an HTTPS URL in your browser, and indeed for every individual hit to the web server. So the public key stages of that need to run once per connection, but there could be a lot of connections in a single web browsing session. So it is important to optimize the performance of that element of things. And there's some interesting algorithms and data structures that are used there. For instance, there's this category of elliptic-curve cryptography, which is one of the most common choices browsers will try to use for this stage of things. And there's a lot of arithmetic going on there, specifically big integer modular arithmetic, which sounds almost like grade school level easy stuff, but it turns out to be rather challenging to implement fast and secure big integer arithmetic. And that is going to be the whole subject of my talk. Okay, but how bad could that be? Well, there is a medium-sized set of algorithms that matter to different, say, internet standards. They're parameterized in various ways, principally by the modulus of arithmetic, a large prime number. There's a moderately large set of moduli that matter for different standards. And then there's a smaller but non-trivial set of different categories of hardware architectures where we care about running these algorithms quickly. So starting or looking back, say, roughly 7 years ago at this point, the standard way to do an implementation is pick a circle from every little bubble in this three-way Cartesian product, and then get one of a small population of experts to rewrite all the code from scratch in C or assembly, because this was viewed as the only known way to get good enough performance. And there are also some security concerns like constant time execution to avoid leaking your secret data through the timing. So that's kind of a bummer to have to take what seems like such a high-level generic thing as arithmetic and re-implement it every time you tweak one of these aspects. So we came up with a better way of doing it. Our framework is called Fiat Cryptography, and the base of it is a library of generic implementations of the cryptographic algorithms. So think of this as some functional programming per element of the leftmost little bubble on the previous slide. These are pure functional programs in Coq. Then come up with the parameters that you care about instantiating them to. These will be large prime numbers. I've shown 3 of the actual most popular ones in this little explosive bubble here. And then we have a specializing compiler that is able to create the, say, C code or Go code or Rust code that is free of the performance costs of explicit parameterization and looks pretty much like what the experts were already writing, but we produce it automatically. And like I said, the library of cryptographic algorithms is coded up in Coq and has functional correctness proofs relating it to the more standard Blackboard level number theory math. And the compiler is written and proved in Coq. By the way, there's an extra part I won't have time to talk about in any detail really, which is a further backend targeting our Bedrock low-level language with its own kind of parallel universe of proof tools, broadly similar to the VST universe. And we also use that as a connection point to formally verified hardware. So we can do this whole cryptographic pipeline and get end-to-end proofs from number theory to almost RTL hardware designs that are running the software that's produced by these earlier stages.
Adam?
Yes.
There was some guy here last week saying the word bedrock. You might want to elaborate on the connection or not.
Oh, is that the Aarhus people?
No, it's the Gregory Malachite people.
Okay. Oh yeah, that's obviously a completely different identifier because it has a capital R in it. So no one was confused about that. That's a company. This is an open source project. And there's actually very little connection between those two these days, though there used to be some connection. Thanks for the prompting to clarify that. Okay. So our Coq-verified compiler is now in surprisingly wide real-world use. In fact, all the major web browsers use this compiler in their build processes, sort of. Most of them just link a library that someone else produced using this compiler. And I don't think any of the teams of these browsers are really dealing directly with Coq code. They just use this compiler that we can extract as yet another command line tool. So the upshot is probably over 95% of secure web connections from browsers are running this code that was actually produced with a compiler written in Coq and with a functional correctness proof. And I'm showing here, by the way, on this slide, just a little partial screenshot of this web page that the first author of the paper on this, Andres Urbsen, my current PhD student, produced. So you can check out that link on the bottom if you'd like to see more information, including what all those little footnote markers mean. Okay, so let me talk about some of the bigger context here, some of which you've probably already seen in a VST workshop, but I'm not sure since I haven't seen the rest. What is this formal methods for cryptography area all about? Well, the gold standard that you always want to wind up with is some abstract security property, like you couldn't possibly produce a convincing signature unless you knew a secret key. Like this algorithm is not going to be fooled except by an adversary that can run in more than polynomial time. Then through a process that I'll call protocol verification, you can establish that a particular mathematical algorithm actually has that property subject to standard assumptions. And then through what purposes of this talk I'll call implementation synthesis, though we could certainly talk about verification as well, we want to come up with your specialized assembly code or C code that is known to implement the mathematical algorithm. So I'll be focusing just on that second part, though the VST team and other folks in the world have done some great work on not just the first of these two arrows, but also composing these proofs together. And I can certainly imagine even literally linking with some VST stuff with the work that I'll mostly be telling you about. So in more detail in that second phase of things, you have your mathematical algorithm, which in the case of elliptic-curve cryptography, a popular choice for the web today, you're working with two-dimensional points, and counterintuitively, these actually get implemented with a four-dimensional point representation, which turns out to pay off performance-wise because you can run fewer division instructions if you do things that way, and division is very slow in commodity processors. So we want to verify that the alternative data structure and algorithm gives you the same or answers compatible in the usual sense of data abstraction. So we do that in this project. Then we have to worry about the arithmetic at the level of individual coordinates of these points. So we break one big number out into a bunch of smaller numbers that are small enough to fit in our hardware registers. And this is really the heart of our project, verifying that all this is done correctly in a generic way. And I'll explain the dimensions of parameterization shortly. And then we have a more traditional verified compiler part that from that level is able to produce your C code. And this is where we have to start worrying about limited precision of bit vectors and other aspects like that. So all these little curved arrows have Coq proofs and they all compose together. Here are two examples of the the outputs of this system. Start from the same algorithm and ask it to produce code for a 64-bit machine on the left or a 32-bit machine on the right. These are both just squaring a number. It sounds like almost the simplest thing you could imagine doing in arithmetic lands. The font size here is chosen, so hopefully you're not too tempted to try to digest this code in detail. But I guess the gestalt impression I'm going for is it's not obvious it's the same algorithm on the two sides. And it's kind of interesting that you could have one algorithm that gets specialized parameters in two different ways that leads to these two. And also sure would be a pain to have to write both of these by hand and convince yourself that you didn't make any mistakes. So let me tell you about the algorithms that we're dealing with here and where some of the key challenges come up. I was really surprised first learning about this area of real-world cryptography that it makes a big difference which prime modulus you choose for arithmetic. The code is actually hard-coded to a choice of a prime modulus, and depending on the modulus you pick, you can get much faster or slower code on commodity machines. So let me explain why that turns out to be the case using an example of a very clever prime that does have good performance in practice. That's 2 to the 255 minus 19. It's one of the most popular ones for web standards. And it's an instance of a pattern called pseudo-Mersenne primes, where you have a big power of 2 minus a small constant. Why is this a good design principle for picking a prime number? Well, let's think about one of the central operations we want to be fast, modular reduction, basically running a mod operation after some other algorithm that produces an excessively wide answer that doesn't fit under your modulus. Like let's say we just did a multiply. And in this example, X is the lower order bits of the multiply output. Y is the higher order bits that we have to multiply by 2 to the K to shift into the right position. This is a double wide multiply result. I want to take a mod operation to shrink it back to fit within our modulus. Okay, so let's do some algebra. Let me subtract and add this small constant C in the right position. Then I'll distribute to get that plus out from under the multiply. And what do you know? Now I found a copy of my modulus in this term. Here it is. I can just cross it out because, of course, the modulus is congruent to 0 in this prime field. So now, surprise, surprise, I can express a mod operation with a multiply by a constant and an add. Those are super fast instructions on commodity machines. So we get a huge win versus needing to literally call a mod instruction. And this is why primes in this shape are favored for internet standards. But let's get into an even lower level of detail. Even those halves, X and Y, in that case, are too big to fit in single hardware registers. In fact, we would wind up using 8 hardware registers, in at least a naive way of representing the result of that multiply before we reduce. We need 510 bits in general. And so we can have a formula like I showed down below here with some ellipses to explain how we can take these 8 digits and shift them into place to represent our big answer of this multiply. So I need to do that mod operation from the previous slide here. But unfortunately, there's a 2 to the 256 in a crucial position where we had a 2 to the 255 on the previous slide. So we can't actually use that reduction trick. And if we pick this natural data structure, I'll call it, of having these 8 different digits, which are hardware registers storing different parts of our multiply result, we can't use the trick from the last slide, and we're stuck with really slow implementation. So what the experts do instead, targeting 64-bit machines, is they break their 510-bit results into 10 digits of 51 bits each. And now we get a 2 to the 255 in the right place, and everything's great. So this is the standard way that, say, a 64-bit machine's web browser will work. What about a 32-bit machine where we might not have enough 64-bit machines to fit all these little 51-bit integers, which, by the way, are already strange for not using all the bits available in the registers? No problem. Let's break each of those 51-bit digits into 2 digits of 25.5 bits each. Of course, we don't tend to have fractional bits available, so instead we alternate between floor and ceiling operations to compute the appropriate bit widths of the digits. And now we have the standard way of doing this on 32-bit processors, which is even weirder than the last example because now we don't even use the same number of bits across digits. So I hope I've at least somewhat hand-wavingly convinced you. We can already think of, for just this single prime modulus, at least 3 examples of reasonable data structures that might be used to represent big numbers. And ideally, we would have a framework that is parameterized on the choice of data structure and guarantees correctness for automatically generated code for any choice of data structure. So that's how our system works. We have this library of algorithms that's parameterized on these decisions of how to break big numbers into many digits, and we'll give you fast C code in the end. And the library itself has a proof that this is always going to be functionally correct. In more detail, when you choose the base system representation, that is providing a parameter to a library of generic operations, which are functional programs. We use partial evaluation to specialize them to the base systems. Now we get much flatter functional programs. Then we can use compiler techniques that are broadly similar to CompCert, for instance, that will produce the actual low-level code. And all these different stages have their Coq proofs that compose with each other. So here's an example of the kind of generic algorithm that's in there. Let's talk about how multiplication actually works rather than just the mod that happens at the end. Let me use a simpler modulus, 2 to the 127 minus 1, which we might represent on a 64-bit machine with a 3-digit representation per number. So let's say I'm multiplying S and T here. Natural way to do that is to basically compute all the cross products across this 3x3 setup. So we get these 9 different cross products, which I've arranged suggestively in columns where the powers of 2 are very close to each other. And the output of this multiplication will be viewed as this 5-digit result, where we just add down the columns to get the different digit values. And then we can use this formula to explain how we would reassemble those digits into the big number, where I've grouped the last 2 with a factor of 2 to the 127, which is significant because that number is congruent to 1 in this modulus. So that lets us actually redistribute those last 2 digits into the appropriate positions of the lower powers of 2. And now we've implemented our multiplication, producing a result that is expressed below the original modulus. So you might imagine, if you thought about this a little more, you could write a functional program that generalizes the algorithm we used here, make it work for any prime number and any scheme for dividing it into digits. So that's what we did. We built that code. We proved it correct once and for all. We did the same for the other arithmetic routines that are important in this domain.
Adam, quick question. Can you go back?
Sure.
Slide. In the middle of that slide, there was one line that had an exponent of 86 rather than 85. Is that a typo, or is there actually some variation in the middle?
No, I think that's just what comes up when you do the arithmetic. And luckily, 85 and 86 are close enough that you can correct for that by, as you can see in the third rectangle from the top, we just multiply by 2 in the appropriate place, and everything's great.
Okay, cool.
All right. So once we have the library of arithmetic routines, we can, well, first understand each one as having a bunch of inputs, some of which we can see as compile time, like the digit bit widths, and some of which we can see as runtime, like the actual digit values. Then we can try to specialize them to particular compile time parameters, effectively fusing those into the code. And then we can algebraically reduce the resulting code to get rid of all the overhead of generic parameterization and get some nice lean code that looks more like a C program even. Now, the nice thing about doing this in Coq is that that specialized stage is really just partially applying a curried function, effectively free. And the reduced stage is not free, but it's at least a standard kind of thing people are used to doing in Coq, where you do algebraic simplification by using one of the term reduction strategies built in to Coq, for instance. Turned out to be actually a non-trivial PhD thesis-sized adventure to get that term reduction process to really work effectively for us at scale. So see Jason Gross's PhD thesis for a clever way of making that work. But conceptually, it's not that big of a lift once you're working in type theory. So here's an example of that specialization process. This definition line and this code is explaining the base system for splitting a big number into digits. It's a function that takes a natural number position and returns the integer that is the power of 2 we should multiply by to represent the weight of that digit. And then that example command down there is for synthesizing an implementation of multiplication in this particular prime field. F and G are 2 input 10 tuples of integers. We're going to get out a 10 tuple that is expressed in this set comprehension style to impose a correctness condition on it, namely that it when you evaluate it, it gives you the same answer as if you actually multiplied the two 10 tuples together after evaluating them. And then we can use a Coq tactic to automatically synthesize the appropriate code here. And what comes out is this, a 10 tuple of this arithmetic formula with some magic numbers in certain spots that we can be glad we didn't have to write ourselves. And we can also be especially glad it's proved to be correct. So this is almost to the final code we want, but we want something like C code or Rust code or languages like that. So final stages, let's assume a big expression like this one came out of the previous stage. We will reify it to a syntax tree, then apply standard compiler optimizations like constant folding, which for this example would shrink it down a lot. Then we apply a flattening phase, which essentially puts it into kind of a normal form where we name every intermediate computation. And now the phase that we run that is not typically found in, say, standard C compilers is bounds inference, or at least the way we use it, I think, is not a normal GCC or Clang thing. Let's assume we knew that the free variables X and Y here are bounded like so. We want to push that information through all the steps of computation, which, by the way, are all going to be straight line code for us in this domain. So conceptually, it's not that big of a deal. We can deduce that this intermediate C has the following bounds, and then the intermediate D has the following bounds. And then we notice, oh, good, C and D are both always smaller than 2 to the 64. So they'll fit in 64-bit registers, but they are also always larger than 2 to the 32. So we're not going to be able to squeeze them in 32-bit registers, or let alone smaller integer sizes. So we'll just assign each of these temporaries to a 64-bit integer type in C, which is going to give provably equal answers to if we were working with infinite precision integers. So in general, we might use many different integer sizes in a single program. It's fairly common to get, say, 128-bit, 64-bit, and 1-bit or Boolean answers in a single run of the compiler, for instance. So again, all these little downward arrows are implemented in Coq in various ways, either proved or proof generating, all the proofs composed together, not just within this slide, but also with the previous steps that I told you about. Okay, so that's the summary of how things work. Let me tell you about how we know that they actually work well in practice. We ran a bunch of experiments using I should mention, we actually extract a separate command line tool as one unified Coq functional program here. And we run it on a lot of different primes. And there's some aspects of this process that are untrusted, specifically suggesting the data structure and algorithm variant. If you make wrong choices there, you can get bad performance for a given prime, but you won't get wrong answers. Oh, and also the compiler might have bad performance, not just the generated code. Sometimes the compiler doesn't finish if you make bad choices. But anyway, we have an automated process that takes in your prime and your hardware target and does the rest of the work for you. But we did need to get a lot of different inputs to use to test this system. So where are we going to get a lot of different prime numbers to use for testing purposes here? What we decided to do was scrape a popular mailing list about elliptic-curve cryptography, where we found about 80 prime number descriptions. And we automatically benchmarked the code that we generated for all of them. And only a few of those turned out to be actually bad ideas for prime moduli and elliptic curves that were probably posted by people who weren't exactly experts in this area. So our compiler would sometimes time out for those. So here's one part of our performance results, benchmarking on all those primes. You're seeing here on a representative crypto primitive, the time of our implementation generated automatically versus the previous best known fully generic implementation, the GNU multi-precision library, which has two variants with more or less cryptographic security. But even against the insecure version, which has better performance, we get a significant edge here. You can see if you read this graph, we're often in the neighborhood of 5 times to 10 times faster than this version, which is, to be fair, dynamically allocating its different number representations at runtime rather than having it fixed at compile time in our case. So this is for a 64-bit laptop. We did the same kind of experiment for a 32-bit ARM-based mobile phone, and we get pretty similar results. So we actually wound up with the fastest known C code for all the elliptic curves at the time that we were running these experiments, at least. Now, what you really want to compare against at some level is not the generic implementation, GMP, but the best handwritten code that was out there. So here's one sample of that. It's kind of like a pessimistic choice to make us look as bad as possible. P256 is one of the most common elliptic curves in internet standards. You can see here that the C code we generated was, with either of the compilers we worked with, generated code faster than OpenSSL's generic C code, and about a factor of 2 off from the handwritten or mostly handwritten, but with some metaprogramming assembly code that was included with OpenSSL. And by the way, we have some more recent work that is getting closer to closing this gap with actual assembly generation from our framework rather than just C generation. But still, there's a gap here. But it's not that big of a one. There's still this was close enough to get some real world adoption. Let me say more about that adoption. We were kind of surprised that there were so many folks out there in popular open source projects ready to use our compiler as opposed to their old-fashioned process. Why would that be? So I think reason number one, that cryptography is a great area to target. I'm sure some of the other VST community folks can attest to this. This is an area of relatively high general paranoia about code correctness.
Community that sometimes actually cares about correctness.
Yep, it's a strange property from an industry perspective, but there's a lot of alignment with what formal methods people worry about in that world. Is someone speaking up? I can't tell. Okay, I'll go on. But there also are competitors out there that rely on verification rather than synthesis. We can lump various VST connected work in that category that really bring the same benefits. So it's not clear why folks would want to adopt our tooling instead. Though I will point out some of our competition, like the F-star based work, does have a significantly larger trusted code base because they're, say, trusting an SMT solver. So that might still be a reason, a purely paranoia based reason for preferring to use our tooling. But let me talk about another kind of reason. There is a lot of handwritten low-level crypto code out there that is today maintained by people who didn't write it and don't understand it and are even quite scared of it from a perspective of having to change it. So for instance, in the boring SSL library from Google that is used in Chrome, among other places, they had a 64-bit oriented C code implementation of the P256 curve. None of the current team members really understood it very well. So they decided, let's dump that and instead start generating a version with Fiat Cryptography, which at least we know is correct. Oh, and while we're at it, we never even had a 32-bit version before. We'll just pass a different command line argument and we'll get the 32-bit version. So this is a really good quality of life improvement for a team of developers who has to maintain this kind of code. Also, there were actually performance improvements that came out of having this tool available. Let me tell you about the scenario where that was the case. They had 64-bit assembly code handwritten for another one of the big, most popular elliptic curves. Again, no idea how that thing works by the current team. But one of the team members had an idea for an algorithm change that should actually improve performance. So then they were able to run our compiler and regenerate code compatible with this new algorithm. And now it was C code, not assembly. So you'd expect a performance penalty. But because the algorithm had changed, they actually got twice the speed of the original version. That involved linking with some higher level C code that used a different algorithm than the old high level code used. So this is a really nice example. We didn't even expect this going in, that you can really get better performance by basically improving developer productivity. And it's maybe a nice bonus to have the proofs associated with things, so you're more ready to trust what this strange compiler spit out. But we might wonder, were the formal methods an important part of this project and why it was appealing to people? Maybe the answer is yes. For instance, at least I like to argue that formal methods are a great replacement for activities like testing and debugging. So maybe we really did manage to produce this new kind of compiler significantly more quickly than if we did quality assurance the old-fashioned way. If so, then that's great. Formal methods were really important for being able to get a new kind of tool deployed more quickly in industry. Maybe formal methods, though, were not crucial here. Maybe what was actually important was just having a new kind of compiler for a new domain, in which case maybe the formal methods didn't matter directly for industry, but then it's great that we managed to verify a production quality compiler using just cheap student labor. We could almost imagine this thing had already been out there and we chose it as a case study. And I think this is still a nice positive result if that's the case. All right, so here's the URL for our project on GitHub. We've had a lot of great pull requests and assorted community interactions there over the years, and we'd be glad to add you to that list if you think this kind of tooling could be interesting to connect to your research or use in some practical setting. And I'll stop here and take any more questions.
Thank you very much. Clap, clap, clap. Questions?
Hi, Adam. You go there. So it's very nice. I wonder, with hindsight, because what you end up with is straight line bit manipulation code, going to translation validation at the end instead of all these proofs of compiler failures in the middle, that would end up being more or less work.
Okay, so I'm suffering a bit from the audio quality there, but I think you're asking about why didn't we use translation validation instead of compiler verification?
Yeah, or how it would be different if you did.
Yeah, so we actually are using translation validation for the newer work that I didn't report on in detail here about assembly. And I think we could probably have done the same for some of the earlier stages. It's not clear how to use that in connection with partial evaluation, which is the crucial early stage of our compilation process. I guess I just have to admit a failure of imagination here. Maybe someone knows how to do it. The later stages of our traditional C targeting compiler, I could believe would work well with translation validation. But there's at least a small performance cost in having to run somewhat duplicative work within your compiler. And as always with translation validation, you might find yourself surprised one day, you run your compiler with a new input and validation fails. It's nice to know that that's never going to happen.
Are you optimizing for like what people know about instruction selection? Instruction scheduling.
Instruction scheduling in the newer work that I didn't talk about in detail here, instruction scheduling and instruction selection and register allocation are important parts of it. And there's a joint optimization problem solved by some tool totally outside of Coq, but then we validate the results with similarly to how CompSert does its register allocator with a checker verified in Coq.
Thanks.
He answered my question.
Good. Thank you, Adam.
Thanks you.
All
Okay,
right.
stop sharing.
And let's welcome